Hello, this is Dr. Scott Denstead, founder of EZWxBrief, your best online source for aviation weather and education. Welcome to episode 20 of EZWxChat, a program to discuss various topics related to aviation weather. Well, welcome back, everyone. In this episode, I hope to cover and let you get a better understanding of how to choose the various different initial data sources for the NOAA's version of the Skew-T diagram. In this particular case, it's under rucsoundings.noaa.gov, rucsoundings.noaa.gov, as you see here in the browser. Now, this is also available through the EZWxBrief application, and I'll show you that in a little bit. But I wanted to cover this so that folks understand what they are choosing for the input data source. Now, at the really high level, we have to understand that a Skew-T diagram is just a kind of, if you think about it, it's kind of a form of a sophisticated graph paper. That's all it is. I know a lot of folks will say, when they look at various different applications, they'll say, oh, is this data from the Skew-T? Is this the data that you can get from Skew-Ts? Well, yes and no. A Skew-T, again, is just a visualization tool. It's not like source data per se. All it is a way to visualize temperature, dew point, and wind as a function of altitude or pressure. And it turns out that you can get that information through a radiosonde, which is a weather balloon, or you can get it through a forecast model. That's a computer program run by the National Weather Service that predicts the weather. So when we're looking at the data here, you're either looking at an observational data point, that's from a radiosonde observation, also called a RAOB, or you're looking at it from a forecast model. Now, there are other sites out there that provide a Skew-T diagram or a tefagram or a Stu-V diagram. All those different kinds of diagrams all basically provide the same information. But the Skew-T diagram specifically is the one that's typically used by most pilots in the general aviation community. Again, all those diagrams I just mentioned plot the same information, just the graph paper looks a little different. But the interpretation is for the most part exactly the same given the data you're presented. And that's the key. When we look at the input data source, when we're looking at something like radiosonde observations, what you're going to notice is that in order to depict a radiosonde observation or a weather balloon launch, all you're basically doing is taking information as that radiosonde is ascending, and you're pulling in the temperature and dew point temperature or humidity at that particular altitude or pressure level, and then just plotting it on the chart and eventually connecting the dots to produce the diagram that you see for temperature, dew point, and then you plot the wind. And those balloon launches are only done twice a day on average. They can be done on a more rigorous schedule. For instance, if there is a tropical system that's about to make landfall, a lot of times they will release weather balloons more often throughout the day. However, in most cases, it's twice a day. Balloons are launched at 11Z and 23Z at various different locations. Now, the locations that you see are not necessarily very high resolution. When you're looking at, for instance, we'll go ahead and pull up the upper air charts here, you'll see that these are the locations that have radiosondes that are launched every single day, twice a day. Now, there are a couple of other locations here that are not listed. They may not launch it every single day, and they may not launch it even every day per se, but there are other locations. So you would have to, at least at a minimum, be able to quickly see that this is not a very high resolution set of data, but it's an important set of data that are used by forecast models to predict the weather. And so these balloons are launched. Once the data comes back via telemetry to the ground, then we can plot those on the Skew-T diagram. Now the initial data page that you get if you go to rucksoundings.noaa.gov has changed quite a bit over the last 20 years. It seems like every few years they make some changes to this. So if you look back 20 years ago, this would have looked way different, although a lot of similarities, but there are a lot more things on this, and they've kind of scaled this down to a bare minimum at this point in time. So you'll notice when you put data in here, you have to choose an initial data source, whatever that happens to be. And then you put in a start time, the number of hours you want to look at in the future, and your potential location. That could be a latitude, longitude, it could be a radiosonde observation site ID, or just an airport location, for instance. And when you're doing this, what you're trying to do is understand what it is, what exactly are you wanting to look at? Are you want to look at something that's going to happen in the future, or are you going to look at something that's happened in the recent past? So the initial data source is what I'm going to focus on right now. And this particular site provides you access to the operational, what's called Op40. This is basically the rapid refresh forecast model that's put out on a 40-kilometer grid. Even though the rapid refresh has a 13-kilometer resolution, they put this out on a 40-kilometer grid for a variety of reasons. One thing, if you're on a 40-kilometer versus a 13-kilometer grid, it's easier to retrieve the data and it's quicker to put on your screen, so it's a faster result. You can also look at the North American mesoscale model. That actually goes out to a total of 84 hours, but for this particular application, they only provide you with 15 hours worth of data, and that's at 3 hourly intervals. Whereas with the rapid refresh model, you'll see that you can actually get hour-by-hour forecasts out to 18 hours, but in reality, they've actually extended that beyond, and I'll show you that in a bit. So the North American mesoscale model covers North America, and as well as the rapid refresh covers basically North America. The other one is the Global Forecast System, or GFS. Now that covers the entire world essentially, but it's on a half-a-degree grid, so it's not really a very high resolution grid, but nevertheless you can get a radius or a Skew-T for Antarctica, for instance. And then the last thing you'll see here that I'm going to talk about is this radiosonde observation that we were just speaking about. So radiosonde observations are the easiest to kind of talk about because we know that they're only at various different locations here, and you can essentially look at a radiosonde observation for anywhere in the world, and you can also go back pretty far in time, I think back to like 1990s from that standpoint. So if I wanted to bring a radiosonde observation for the closest to where I am here at Greensboro, GSO, I would simply put in GSO here, and then I would choose the time I want. And so the latest one was from this morning here on September 14th at 12Z. So even though this radiosonde is launched at 11Z, they call that the 12Z launch. Same thing with 23Z, they call it the 0Z launch. So you'll put that in here and you'll choose RayOb, and then you'll click the interactive plots for that, and it should bring up the radiosonde observation. You see the R there, which stands for radiosonde observation, and again that's valid at 12Z. Again, even though it's launched at 11Z, it takes a while for that radiosonde observation, roughly 90 minutes, to reach the top of the atmosphere. In this case, it looks like it went all the way up to almost 103,000 feet here before it became as big as a two-car garage, burst, and parachuted back to Earth. And so from that standpoint, you can see the temperature and dew point trace as that radiosonde ascended, as well as the wind here on the right for that particular date and time. But if I wanted to look at, for instance, and go back and look at what was happening, let's say in February, let's say February the 14th, or let's say 13th here at 12Z, I could do that. Add GSO, click on interactive plot, and it will give me something that's happened in the past. And we see a nice, interesting kind of temperature inversion, almost what we consider kind of close to a freezing rain profile here up in the Greensboro area on this particular day and time. So that's the way you would deal with radiosonde observations. That's one initial data source here. And then we can look at forecasts. And so the one I generally use almost all the time is the OP40. It's the operational version of the rapid refresh. It used to be the RUC model, the rapid update cycle, and that's the term that you see up here, RUC soundings. They decided not to change it when the rapid refresh became the model that replaced the RUC, but nevertheless it is the operational version of the rapid refreshes, whereas the back 40 is a experimental version. It's the GSL version that's running. This is run out of the Earth Systems Lab, GSL. So as a result of that, they actually run that as well. And sometimes you'll see some cases where the back 40 may be available where the operational may not. So the best thing to do is look up here at this line, and essentially can tell you that the latest analysis for the OP40 is 17Z, but actually the back 40 analysis is a little bit newer, fresher. So if those are red and not green, most likely you're dealing with older data. So pay attention to that as well. And so the operational 40 of the operational or OP40 is typically what I would be using most of the time. And we'll show you how to get to some other models in just a bit. But I will put it in here, and I'll just say let's look at GSO, and let's go back to the latest run of the model. Make sure that latest button is clicked. It's defaulted to latest, so that should be fine from that standpoint. And don't worry about this desired forecast projection. Just leave that alone. And then you can put in the number of hours you want. So the rapid refresh, generally it says out to 18 hours, but I know it goes out further than that. So let's put in, let's say, 48 hours of time. It doesn't go out that far, but essentially let's see what happens here. So we put an interactive plot here, and what you're going to notice is that it will come up and it will go out and pull out hour by hour for that particular location here, GSO, and actually you see, wow, this actually goes out to F50. That's a new thing. Normally it would only go out to somewhere around, let's say, 38 hours or so. It looks like they're running it even further. So that's exciting. It's nice to be able to get these kind of forecasts out even further than that. And at some point in time, I know they're looking to extend the rapid refresh model to have it run for longer forecast hour-wise. So this actually goes out fairly far in the distance, and it is kind of an hour by hour. So there's the 31 hour, 32, 33 hour, 34, all the way out to that. So just out of curiosity, I'm going to see what. Let's go out to, let's say, 84 hours. Again, they even though they say 18 hours here, it may not necessarily always be the case. So let's see how far it goes. It may only go out to 50 as well. Yeah, it looks out to 51 is the furthest it goes out in time. That's 51 hours. That's over 2 days out in the future. Again, that's pretty nice to be able to have that. But again, it provides you with hour by hour. So let's say you're just only interested in what's happening over the next 12 hours or so. So you're making a flight and you want to notice what's happening over the next 12 hours. Then you would put 12 in, and again click interactive plot. That way it gives you information for GSO at that particular location and over the next 12 hours. Actually, it's 11 hours worth of forecast, and the first one that always comes up is called the analysis. That's the initial conditions of the model, and it's always going to be valid in the recent past. And you notice the OP40 analysis now is updated to the 18Z, so it's the fresh version of the rapid refresh, the newest, say, version, the newest run of the rapid refresh model. And so the model here is just not an interpolation of all those radiosonde observations that we were looking at further. I get that all the time. Folks say, "Oh yeah, it's it's just an interpolation of those balloon launches." It's not actually. Interpolation would mean essentially that it would only be able to figure out what's happened between these different balloon launches. In reality, this is the rapid refresh is a predictive model. It's a deterministic model, so it's able to determine what's happening at this location, and the radiosonde observations are just one of hundreds of thousands of data sources that are used in these models. So this is not just an interpolation between various different balloon launches. It's way more sophisticated than that. If it were, it would be pretty much useless. Instead, it's actually trying to figure out what might be the case based on some very sophisticated equations of motion, and therefore providing you with really good information from that standpoint here. All right, so if we also look at the other back 40, again, the same thing can happen here. Let's go ahead and put this out to 84 as well. And we'll see how far that goes out. And it doesn't go out as far. It only goes out to 18 hours here in this particular case. So again, I wouldn't necessarily spend a whole lot of energy trying to figure out what the differences between these two are. Essentially, I would stick with using the OP40 for now as your primary data source. But if you wanted to see what's happening out a little bit further in time, the GFS, it actually goes out to 16 days, but they restrict this. So if you put in here, for instance, let's say 200 hours, for instance, just to see, and go out further for the GFS, what you're going to notice is that you're not going to get 200 hours worth of forecast. It actually stops at 84 hours. Unfortunately, that was because there was somebody abusing this and trying to automate this in a way and trying to get forecast out to much longer in time, and it was basically bogging down the server, so they had to limit it to 84 hours, which is unfortunate. That's only 3.5 days out. You would want to see this, the GFS model does pretty well even at 5 days out in the future, but for this you can only go out to 3.5 days in the future. So from that standpoint, if you're trying to look at that, plus, or maybe you're in Australia or you're in Europe and you want to see a Skew-T diagram for an airport there, you can certainly do that. Or if you're making a trip, let's say up to Iceland and Greenland and over to Europe, or even the other way, this allows you to basically see diagrams in that region as well, basically outside of North America. So I could actually put in here any city or any airport in the world, and it will come up with a Skew-T diagram for that particular airport. Again, this is a forecast. Now the other thing you'll notice is that when you pull up these forecasts, you'll notice at the very top here, this says 5.4 nautical miles, 207 degrees. It's not really at GSO, it's actually 5 nautical miles on the 207 degree radial from GSO. So it's the closest grid point. The idea basically is that the data is put onto a grid, a matrix, and that matrix is what is used, and essentially it's finding the closest grid point to show there from that standpoint. So again, the GFS model will give you an 84-hour forecast. So that's what you'll use for longer range forecasts beyond what essentially is now looks like almost over 48 hours with the OP40 is available. And again, that may not be the case for every single run. A lot of times they may run this to longer hours at, let's say, the 18Z run or the 0Z, 6Z, and 12Z runs. I actually don't know what their algorithm is per se here. And as a result of that, you may find that if it's the next run, which is the 19Z run, you may find that that's not the case. But I have seen it out regularly out to 38 or 39 hours in the future. And so the other aspect of the GFS model, if we go back and look at that again, put in 84 hours here, put in GSO, is that you'll notice that the resolution of the forecasts are essentially 12Z, 15Z, 18Z, 21, so it's every 3 hours. Whereas when you are looking at the input data source for the OP40, you'll notice that it's actually every hour that you'll see. So the resolution is a lot higher, which is more useful to us. And for the most part, you're going to see that the actual data point, the grid point, is going to be a little closer to the sites that you're putting in than you would with the GFS model. But you can see here this is a 32, 33 hour, 34, 35. So it's hour by hour forecasts that are available to you there. And so the other ones here, retro or sims, is not something that we want to utilize. In many cases, you have to have special permission to use those. But for this particular situation, you're going to use OP40 the most, or use the GFS, or if you want to see actual data. Remember, radiosonde observations take a while, so if you're looking for the 12Z radiosonde observation at 1201Z, you're not going to get it. Most of the time, it takes an out from 11Z when it's launched. It takes about 90 minutes for it to ascend to at 100,000 or so feet, and then it takes a while to process that and actually show up here. So you're typically talking 2 to 3 hours after the launch time where you'll be able to see it. Whereas the OP40 gets run every single hour and refreshed every hour. The GFS runs every 6 hours, but the OP40 runs every hour, so it's usually refreshed somewhere around near just shortly after the top of the hour. It takes about an hour to run, and so you'll have data for the next run. So the next time that we see the 19Z run will be a little less than an hour from now at this point in time, because we just had the 18Z run complete. Now in Easy Weather Brief, I'll briefly talk about that. Basically, to get to the Skew-T diagram, I've made it possible. So if you go to Start and you go to View Airport Weather, what you'll see in the airport page here is you'll see this kind of hierarchical symbol icon there, and in there you'll see Skew-T diagram. And what that'll do is that'll open up a separate new web browser where you can then at that point in time see the way it's designed here is that it shows you essentially the analysis plus out to 19 forecast hours. But you can then decide if you want to look at the GFS model from here. You can just go in and do a load soundings button here, and then you have access to a lot more models that are not on that main page. Now, not all of these are necessarily operational or even important. You can go to the GFS here. One of them I like to use is this RAP 130, very top one here, and use that instead, just because it's going to have a lot higher resolution. Now we're not talking about a 40-kilometer grid that this is being used on. Instead, this is being used on a much higher scale. So, so you could actually do that as well, and it will hopefully provide you with that, although I'm seeing right now it's not necessarily. It evidently does not like that selection here. It's the latest run, 20 hours of loading. Let's just do 18 hours here. and running on this one. Well, let's try this other one here and load that. Yeah, there we go. So that second one, and I'll show that again so you can see, is going to have, this is 5.8 nautical miles. So you can see as you update this, it's 3.3. It's going to get a little closer to your point, and that may make a lot of sense, especially when you're looking at an airport that may be near a large body of water, such as an ocean or a river or lake, or even a mountainside. The idea is you don't want to be looking at a data point over the ocean. It necessarily means that you're going to probably interpret that a little differently than interpreting it if it was right over land, because over oceans you probably have you may have it sometimes in the day, you may have a nice temperature inversion. Right over the ocean it may be cooler in that lower part of the atmosphere, so it may change things. So it's important to notice where that is located here. But you get to that one is the essentially the RAP Ops 130. That's the second selection here. So you can see that the RAP 130 itself doesn't do anything, and that's going to be the case for some of these other selections that you see here. You may not be able to get all those that are available for that. So for instance, if I go to the high resolution rapid refresh and load that, it doesn't do anything. For whatever reason, that particular selection is not active at this point in time, and probably never will be. They just need to update their, but at least at a minimum it gets you access to this RAP Ops 130, which is a higher resolution product from that standpoint. And so you can get a pretty good idea based on looking at the various different sites here. So I can go to KGSO, pick that, and then at that point in time I can then look at the GSO observation. Brings up a new window and say observation, the analysis, and then forecast for the next 19 hours beyond that, and that allows me essentially to analyze that as well. So that's available within the Easy Weather Brief application. And so when you look at data like this here, this data that you're showing here, this actually, it's built from several different forecast models, not just the GFS, not just the rapid refresh, but it's actually a blend of other data, but it should match pretty closely in time and space for the Skew-T information that you were looking at. So for instance, if I wanted to kind of examine at this particular location for GSO, and I wanted to look at, see what's happening here, let's say at 2,000 feet, at 5,000 feet, at 8,000 feet, and look at the wind speed and direction, it should be pretty close to what you would look at a Skew-T at 18Z or so. It's just presented in a slight different way. Again, the Skew-T is just a visualization tool, just like this meteogram is a visualization tool from that standpoint. Okay, so that completes episode 20 of Easy Weather Chat. My name is Dr. Scott Denstead, and as always, I hope you enjoy the simplicity of Easy Weather Brief.